Hey everyone, this is Mohammed Nadeem and welcome to my YouTube channel. Today in this lecture, we will discuss in more detail about the RLC series AC circuit. This is actually the resistor having resistance R, inductor having inductance L, capacitor having capacitance C. These three components are connected with each other in series and they are also connected with the applied alternating voltage source. As we know that in pure resistive circuit, the current I and V are both are in phase with each other. This is the phasor for the current I. This is the phasor for the voltage VR. And here the angle theta is equal to 0. Therefore, we can say that these two phasors are in phase with each other. In pure inductive circuit, the voltage VL leading the current I by 90 degree. So this is the phasor for the voltage VL and this is the phasor for the current I. This phasor VL leading this current I by 90 degree. In pure capacitive circuit, the current I is leading the voltage VC by 90 degree. So this phasor diagram for the current I is leading the phasor of the voltage VC by 90 degree. So such a sort of arrangement is present here in this simulation. In this simulation, we have this is the pure resistive circuit, this is the pure capacitive circuit, the pure inductive circuit. Here, this is the source for the alternating voltage, and here the voltage of this source is 35 volt. The frequency is 0.25 hertz, and this is that same source having same voltage, and this voltage this source also have the same voltage 35 and the frequency is the same. So these all applied voltage source have the same voltage and frequency. And here this is the pure resistive circuit, and here this red colored arrows represent the conventional current. As we know that these alternating voltage source are changing their polarity with respect to time. So therefore, these charges present inside this conductor will move from one side and then again it's change its direction and move in the other side. So in other words, we can say that the electrons or the charges inside this conductor will vibrate about their mean position, which represent actually the sinusoidal wave, and sinusoidal wave represent us the change in magnitude and direction at each in one cycle. Here in pure resistive circuit, the voltage V and the current I both are in phase with each other. But here we have that same applied voltage source, okay, and now we have different component of this circuit. So here if we compare these two, the electrons having some phase difference, okay, the current having some phase difference. So now this is moving in this direction and here it has the other direction, so there is some phase difference. It means that if we have even the same source, okay, the current may be different, okay, it depend upon the component present in the circuit. So therefore here we say that the voltage V is lagging behind the current I in the pure capacitive circuit. Here this current I is lagging behind the voltage VL by 90 degree. So what will happen if we take these three components all together in one circuit? So then what will be the behavior of the electrons and voltage in that circuit? So we have that same scenario here. Okay. We have this resistor having a resistance 10 ohm. This is actually the inductor and this is actually the capacitor. If we connect these three with each other, okay, in the same circuit. So therefore there must be some phase difference present between the voltage and the current. So here in this same lecture we will determine that phase, okay, and we will also determine the voltage V, okay. So we have this voltage which is equal to V is equal to Vm sine omega t, and if we applied this voltage in the series circuit, so this is actually the series circuit. In series circuit, the current I is the same and the voltage V is different. So this voltage V will be will be distributed in these component of the circuit. So some of the voltage will be go to from this component, and the sum will be provided to this component, and some will be provided to this component. So if we again add the voltage of these three, it will give us this. So in this same lecture we will find the voltage of the resultant voltage present in this circuit and the phase difference between the current I and voltage, the resultant voltage V. This is that same circuit diagram which I have discussed in the previous simulation, and this consists of the resistor, the inductor, and capacitor. These are the phasor diagram for that. And now we are interested to find the resultant voltage. So for that we will add this VR, VL, and VC. These are considered here in the form of the phasor diagram. So therefore we will apply the vector algebra, and in vector algebra if you add some vectors you will apply the head to tail rule. So for that I'm going to first take this vector and we bring that to here. Now we will take the tail of this second vector and we'll put that with the head of that last vector, okay, and it will give us this VL. Okay, this blue color is actually that VL. Okay, now this blue color is that VL, and now we will take this last vector, okay, and we will put the tail of this with the head of that last, okay. So we will take the tail of this with the head of that last, uh, and we will put the magnitude in such small amount. Why this magnitude is small amount? So here this diagram we consider at higher frequency. At higher frequency, the we know the relation for the capacitive reactance, which is equal to 1 over 2 phi fc. So when the frequency is higher, here this denominator will be higher, due to which this xc will be less, and from here xc is directly proportional to vc, so due to which that vc will be less. And this XL, the inductive reactance, is equal to 2 phi FL. So if we increase this F, this XL will be more, and from here this XL and VL are directly proportional to each other, so therefore this VL will be more. So from here in this diagram we will take the magnitude of VL is more and the amplitude of this VC is less. In other words, we can say that at higher frequency, this circuit will behave as a pure inductive circuit. Okay, so here we have that same scenario. So we will subtract this VC from this VL. So if we subtract that, it will give us this only. This is actually the VL minus VC. So therefore, I have put that in this side as VL minus VC. So this triangle will be formed here. So if I draw it here clear, so this is actually that phi. In this side we have the VR, and on this side we have VL minus VC. Okay, so VL is up to here. Okay, VL is up to here, and this resultant is drawn up to here. Okay, so therefore we take this side as a VL minus VC, and now this is the resultant, and we know the resultant will start from the tail of the first vector and will join the head of the last vector, and this is the resultant. And in this case the resultant is actually that applied voltage source. Okay, so therefore we put here is a V, this V, and this is the triangle for date. Similarly, at low frequency, this X is equal to 1 over 2 phi Fc. So if this F is lesser, then this Xc will be more. And from here, Xc is directly proportional to Vc. So due to which this Vc will be more, and the magnitude of this Vc will be higher. It will be more. Okay, and the magnitude similarly XL is equal to 2 phi FL. So if this F is low, then XL will be low, and due to which this VL will be less. And therefore in this diagram we have that VL with the less magnitude and VC with the more magnitude, just opposite of this. Okay, so we have that voltage VR, this VL but with the less amplitude, and this VC, but now the magnitude has increased, so that is that VC. So this VL is in opposite direction to this vector. So we will subtract that. So if we subtract that, so it will go to here, to this point. Okay. So from here to here, this is equal to VC minus VL. So this whole is VC. If we subtract this VL, so it will go to this point. So therefore, from here to here, this is the VC minus VL. So now we have to, this is that same scenario. We have that triangle. This side is VR, this is the phi, this is the resultant V, and this is the VC minus VL. And at resonance frequency, the VC will be equal to VL. So here we have that same VR. Okay, and this side we have the VL, on this side, on this side we have VL, on this side we have VC, and we taken this current as a reference. So we taken that current as a reference, and according to with respect to this current, this is in upper side. Okay, so this is in upper side, and here this VC is the is in a lower side of this reference current. Okay, and that is in lower side. So these vectors are in same in magnitude but in opposite direction. So therefore they will cancel each other, and the resultant here will be this VR, which is in phase with this current I. So therefore when at resonance frequency, this scenario will behave, this RLC circuit will behave as a pure resistive circuit, and at low frequency this RLC circuit will behave as a pure capacitive circuit. At higher frequency this will behave as a pure inductive circuit. Now in this lecture we will consider this pure inductive the behavior of RLC as a inductive circuit. So at higher frequency this behave as a inductive circuit. Now we have this same diagram here. Okay, we have that same diagram here. Now this is the diagram for the RLC circuit but with the higher frequency. This is that resultant V, voltage V, and this is VR, this is actually VL, and this is VC. And from here from here to here, this is VL minus VC, because we subtract this from there. This is in opposite direction having less magnitude, so we subtract that here. Okay, Now, at higher frequency, we are interested to find the resultant voltage. We are interested to find the magnitude of the resultant voltage. So, for that, we will apply the Pythagoras theorem on this triangle. So, according to that Pythagoras theorem, uh, hypotenuse whole square is equal to base square plus uh, perpendicular square. So here the hypotenuse is actually that resultant V. So that V square is equal to base is here is VR, V of R whole square plus perpendicular here is this VL minus VC. So VL minus VC whole square. Now, this V square is equal to the value of VR is this, which is equal to IR. So, instead of this VR, we will put IR into whole square, and instead of this VL minus VC, okay. So, this VL is equal to this I XL minus this uh, XC IXC whole square. Okay, so now this is equal to V square into I square R square plus here we have that I XL minus I XC whole square. So from here we will take that current I as a constant, okay, and if we bring that out of this square, it will be I square here, okay. So here we will take the square root, so this side will become V, and it is on that side it is equal to uh, I square into R square plus we take I square. I is a constant, and if we bring that I out of this square, so it will become I square. So it is equal to XL minus XC whole square. Now this V is equal to here that this V is equal to square root of now we will take the I square from these two, so it will become equal to I square. We will take that common, so it become R square plus R square plus XL minus XC whole square. So this square root and square will be cancelled, and here it will become this into I and square root of R square plus XL minus XC whole square. This is the relation for the resultant magnitude of the resultant voltage. And now we are interested to find the total opposition upward to the flow of the charges in this RLC circuit. So for that we know from the Ohm law that V by I is equal to R. So therefore that above equation will become this V by I, and on this side the remaining thing will be R square plus XL minus XC whole square. Now this V by I is the is actually the resistance. Okay, but here we have three components. One is the resistor, the other one is the inductor, and the other one is the C. So therefore, we call this resistance as a uh, Z, as a impedance. So in that case, we call this as a impedance, and which is represented by Z. This Z is actually the total opposition upper to the flow of the charges in this RLC series AC circuit. So instead of this V by Z, we will put this Z, okay, and which is equal to square root of R square plus XL minus XC whole square. So this equation 3 is for the impedance, for the resistance uppers to the flow of the charges. Okay, we will determine the expression for that phase. So let's say for that we know that the tangent theta, tan theta, tan phi. In this case, we have this phi, which is equal to this perpendicular divided by base. Okay, here perpendicular is VL minus VC. VL minus VC divided by the base, and base is the VR. So this VL is equal to IXC. IXL minus VC is equal to IXC divided by this VR is equal to IR. So from that above we will common that I, and it will become XL minus XC divided by I into R. This I and I will be cancelled, and it will become XL minus XC divided by the R. Okay, this is actually that angle phi. Okay, so by this angle phi, the current I will be lagging behind that resultant voltage. The voltage VR will be lagging behind that resultant voltage R, and here this VL minus VC will lead that resultant voltage VR. Okay, so this is actually that angle phi. In this diagram, we know about this VR, we know about VL minus VC, and we determine the expression for the magnitude of this resultant voltage, and we also determine this angle phi. Okay, so this was the explanation for the RLC series AC circuit. So in this RLC series AC circuit, when the voltage V is applied, okay, here we have the voltage VR. So this V will lead that voltage VR. Okay, this voltage V will lead that voltage VR. And here, when that pass through these components, that same voltage V having magnitude this, okay, will lag behind that VL minus VC, and that same voltage V having magnitude of this will they will lead the current I by angle phi, and that phi is given by this. Okay, that phi is given by this. Okay, so if we know about the XL minus XC, XL and XC and R, then we can easily find the resultant voltage and the angle phi here. Okay, now we will discuss about the power factor. So the power factor is equal to the true power, which is actually the power consumed in the circuit divided by the apparent power. So the true power is equal to Vi cos phi divided by the apparent power, which is equal to Vi. So this Vi and Vi will be cancelled out. So here cos phi is equal to so it will be equal to cos phi. So if this and this is cancelled here, okay, so it will be equal to cos phi, and we know that cos is actually the base by hypotenuse. So here we have in this same diagram, in this diagram we have the base, which is Vr, and the hypotenuse is V. So this V is equal to IR. So instead of that we put IR, and this is equal to V IZ. Okay, Z is actually the total impedance up, the total opposition upward to the flow of the charges, and this is actually the total voltage. So instead of that we put I Z. This I and I will be cancelled, which is equal to R divided by Z, and we know the value of the Z from this equation 3. And if we put this in the upper side, we have the R, in the lower side, in the denominator we will put the value of the Z, and which is actually that equation 3. So equation 3 is equal to square root of R square plus XL minus XC whole square. This is actually that resultant power factor. Now here are three conditions, and I have discussed that in the first condition, if XL is greater than XC, then XL minus XC will be the positive, and it will in this case the RLC circuit will behave as an inductive circuit. So this condition is present here. In this case, this XL is greater than this XC. So therefore here this circuit, this RLC circuit is behave as a inductive circuit. In the second case, if XL is equal to XC, XL minus XC will be 0. So that circuit will behave as a resistive circuit. Okay. So when XL at resonance frequencies, so here at resonance frequency, if Vc is equal to VL, so here this Vc is equal to I XC, which is equal to I XL, and this I will be cancelled. So here Xc is equal to XL. Okay, so when in at the resonance frequency, when Xc is equal to XL, and in other words, when Vc is equal to VL, this Vc and VL will be cancelled out, and here is the phase difference between the voltage and the current will be the same. They are in phase with each other. So in this case, this RLC circuit will behave as a Phasor resistive circuit. And at this last condition, if XL is less than XC, okay, so when XL, this XL is less than this XC, then in this case the XL minus XC will be the in this case the XL minus XC will be the negative. Okay, and this circuit will behave as a capacitive circuit. So this will behave as a capacitive circuit. So these was the conditions about the RLC circuit. So first we start from the circuit diagram of the RLC circuit, and we determine the resultant, we determine the total voltage in that case by adding these phasor diagrams, and we consider that same circuit diagram at higher frequency. At higher frequency, it behave as an inductive circuit. At lower frequency, it behave as a capacitive circuit. At resonance frequency, this same circuit is behave uh, as a resistive circuit. Okay, so now, first, we determine the resultant voltage by adding VR, VL, and VC, and that addition is present here. So, now it give us this diagram, okay? And if we apply the Pythagoras theorem on this diagram, it will give us the magnitude of that V, okay? The magnitude of that total voltage V. And after that, we are interesting to find the angle phi, which is given by this, okay, 10 phi, okay, and this is actually the total opposition upward to the flow of the charges. Now, this is the main diagram here, okay. So in this diagram, in this diagram, we have that resistor R. This is actually that total voltage V, and if we apply that to this circuit, that will pass through here, this resistor R, and here we have the voltage VR, and this voltage will leading the voltage VR. So by how much angle it will lead, so that is determined, that is given by the tan phi. So this resultant voltage will be leading this VR by angle phi, and here this resultant voltage will be lagging behind VL minus VC by angle phi, and which is given by this tan phi. And here in this circuit we will have some current, and that current is the same through all components of this circuit, and this current will have some phase, and the phase of this resultant voltage will be leading the phasor of that current by angle phi, and we have the angle phi is given by this tan phi, and this is the power factor, and these are the condition for that. And this all was the explanation for the RLC series AC circuit, and that's it, guys. Thanks for watching.